All right. Hello. So I'm also Piotr. And actually, I have a confession to make because I've spent over a decade working with .NET before I finally transitioned into Rust, which was like 2 years ago. I don't remember the exact reason, but it just went this way. But jokes aside, I find actually C# to be a pretty good language to work with. And during the last few years, when I was still using C# at work, I had the chance to play with different kind of messaging and communication protocols, let's put it this way, like Netty, ZeroMQ, RabbitMQ, RabbitMQ Streams, Kafka, of course, or even the Aaron, which is quite heavily used when building some low latency trading financial platforms. So at this time, I was actually wondering, what would it take to build your own messaging or actually streaming platform? We'll get into this, what is the stream, in a moment, from the ground up, because some of these tools were either too slow or they were very fast, but at the same time, very complex to set up, very difficult to use from the programmer's perspective. So having this desire to actually learn these messaging internals, having the willingness to learn Rust at the same time, and being the owner of two lovely Italian Greyhounds, I decided to start with a pet project. And I called this one Iggy as the abbreviation of this Italian Greyhounds. And what happened later is that it started as a pet project, and here we are 2 years later. Just recently, we got, let's say, transitioned under the Apache Foundation to the incubator program, just to ensure that it will remain the free and open source software forever for the community. And while this talk won't be about this project itself, I will be actually sharing all this experience we've gained while building this project from the very ground up. And I'm saying we because it's not me, it's actually quite a few people. There's like, I would say, 5 of us working on this on a daily basis, after hours, of course, and lots of contributors from all around the world. So just a few words about this project itself, this streaming platform written in Rust. So if it's Rust, it must be blazingly fast, right? That's obvious. We support different kind of transfer protocols like TCP, QUIC, which is UDP, HTTP. We have very high throughput, and we are working on making very stable tail latencies because actually it matters a lot how well your system can handle high demand, very high throughput, if it just doesn't start lagging out of the blue. On a single node, we can achieve like easily 5 gigabytes per second writes. I was able to achieve 15 gigabytes per second reads without any caching. We have very cool community. We are working on SDK for multiple languages. And actually, we made this benchmarking, this process of benchmarking the performance, this kind of regression testing, our first-class citizen. So we can see if all these changes that we implement in the code base are actually making this project more performant than it was, right? So this is like one of our core principles, to make it as fast, as efficient as possible. And we've got a bunch of tooling built into this project, which of course, all these tools are open source as well. We have CLI, we have dashboard to browse your data. We've got another CLI for benchmarking. We are yet to build another CLI with Ratatouille. that's going to happen for sure. And we also even build this open platform where we share our benchmarks, and you can simply, let's say, see on your own or even send your own benchmarks to us with all the latencies, all the throughput that you can achieve on a different kind of hardware, different kind of cloud environment, etc. But let's get back to the main topic. So what is the stream? Well, you could say that the stream is just a continuous flow of data being exchanged between your applications, whatever that means. But from the technical perspective, it's nothing more than a very simple data structure, so-called append-only lock, where you simply append the data on top of it, right? And you just have a bunch of records, potentially millions or even billions of records, appended in this specific order from the very left to the top. And of course, at the very top, the head is the latest data, right? So this is just like a very extremely simple kind of database. So that's pretty much the stream. This is what the stream is all about. And what it gives you in terms of, let's say, processing the stream or reading the stream is that since it acts as a simple database, you can have multiple independent consumers consuming this data in parallel, right? Because as in opposite to, for example, using the regular message broker and a message queue, which works in this first in, first out semantics, you don't actually need to, let's say, copy the same message across multiple unique queues and then this message would be picked up and deleted from the queue to be processed by the consumer. You have a stream of data, and your consumers, they simply have this thing called offset. So this is pretty much what we call this indexless position of the element. They keep track of their offset, and they can browse, replay the data in whatever order they want to do this. So that's pretty much all about the stream. And well, you might be wondering, so how is it actually possible that I am here talking to you, and that's me, and there's other people, other devs on the core team, and other people from all around the world, and we've spent 2 years already building this, and there is more to come, right? I mean, this sounds nuts, right? Who could spend 2 years on building this? It doesn't make sense. So let me explain myself, and we'll start with the very basics. So we'll try to build a very basic hello world stream, and then we'll move on to some interesting optimization techniques that you can actually apply to building any kind of infrastructure or even your applications. So let's begin. So the stream will consist of, let's say, 3 fields. It will have some sort of unique identifier, as we might have multiple independent streams. It will have this offset, so the current offset, current position, so how many messages are there, what's the latest offset, and of course the path, since this will be a durable append-only log. So the stream is persistent, right? It's kept somewhere on disk, so it's not running somewhere in memory. It's not just an ephemeral thing. And the message itself, we only have an offset. It will also have the payload, so any kind of raw bytes data sent to us by the client. We don't care if the client's using JSON, BSON, protobuf, whatever, just any kind of raw data. So speaking of the stream, we'll have 2 methods. So we'll be able to append data to the stream, and we'll be also able to pull the data from the stream. So when we talk about, let's say, getting the data from the stream, we're talking about polling. So once again, in a regular message broker model, the messages are being pushed to you. So we have the push model, while in the stream, let's say, approach, we use the pull model. So the client is responsible for pulling/fetching the data on his own. So all the things like dealing with the back pressure, these sort of things, it's all on the client. So from the server perspective, you don't really care about it. It's all on the client. So we have these 2 methods. And, well, let's start with the message. So we're going to build our very sophisticated serialization mechanism for the message. So we have a byte array. We're just going to include the offset, the payload length, and the payload, right? And this is our message serialized into raw bytes. At the same time, we can deserialize this message. So we'll just take first 8 bytes, as we're using just a 64 unsigned integer. This is an offset. Then we have the payload length. Then we have the payload. And voila, we have a message back, right? So no need to use even a SERDI at this point. Just a very simple deserialization mechanism built by ourselves. So if you were to store this somewhere on disk, this is probably how this could look like, just some binary data stored on a disk, right? And, well, so how do we append this data to the disk? So at first, we, of course, need to increment the offset. Also keep in mind that just like in a regular, let's say, array, we start from 0. So if this is going to be a very first message, we just need to check. If this is a first message, then it's offset equal to 0, otherwise +1. We're setting the current offset to the server offset, and we are just, serializing the message to the raw bytes, opening the file, opening our stream file path, and just appending these bytes to our stream stored somewhere on disk. And at this time, well, you might notice that it's probably not the most durable or reliable solution, since it's potentially possible that somewhere at this point when we are calling write all, well, the hardware might crash or the virtual machine might be turned off. So we might want to just include fsync here, right? Just to ensure that this data will be actually flashed to the disk at this time, just to give our customers, the users of our server, this very strong durability semantics. So we could just call fsync here. But the issue with fsync is that it can dramatically reduce our performance, like order or magnitude, or even 2 orders of magnitude, which is a lot. And we probably don't want to do this, at least at this point. So even if you read like Kafka documentation, they will give you some hints that maybe it doesn't make much sense to use fsync for every message. Just try to do something in between. So one of the things that we can do to improve this is that instead of just storing the data after each received message, we could just as you can see here once again, include this batching approach. So whenever we receive the message from the producer application, whether this is a single message or 1,000 messages at once, we might have some configure limit on the server, as you can see here. So whenever we receive these messages, we just add them to our in-memory buffer. Let's call them unsaved messages. And we simply check if this buffer, whether this buffer has reached, let's say, 1,000 threshold of total length. If it didn't reach this threshold yet, then just return. Otherwise, if we reach this threshold, let's just serialize all these messages at once and only then sort them to the file, right? So we have the simple batching to sort of mitigate this potential fsync issues at this point. But you quickly realize that you might get into trouble, because what happens if you're not receiving any additional messages and your buffer just keeps there waiting, right? Just for 5 minutes. Probably not the best idea. So at the same time, just looking at the Kafka docs, you might notice that, well, they also tell you that it might be a good idea to have some additional flash interval here. Well, the flash interval is nothing else than just some background task, which is triggered, let's say, every few milliseconds, few seconds, whatever you decide to do. And this will look for all these buffers with unsaved messages in memory and just flash them into the disk. So we have these two small optimizations, which actually can dramatically improve our overall performance latencies. So we batch the messages, and we have this additional interval, saving these messages when the time has come, which still isn't perfect. And we'll get back to this topic later on, like how can we deal with fsync, or how can we maybe even get rid of fsync, because it's not as perfect as it may be. But at this point, let's just stick to this batching and background saver to mitigate these fsync issues. All right, so let's move further. I mean, in an ideal world, if we would like to run this on a production somewhere, we would, no doubt, we would need some clustering feature in place. We would need a way of replicating this data across multiple nodes, multiple servers, so that if one server dies, at least the data still lives on the other server. So whenever you work on some actual product and there's lots of data in it, maybe you're using some database, whether it's Postgres, Mongo, doesn't matter. Most likely you have some kind of replication behind the scenes, right? Just not to lose all the data if the server or virtual machine just dies. And of course, replication and clustering itself will give you this very high availability and very high reliability. But at the same time, there is quite a complexity to implement this right. And even though there are some well-established solutions like Raft, Paxos, view-stump replication, it's probably not the scope of this talk. This is quite a huge topic. But anyway, we would need to have the clustering at some point to make our data actually not just scalable, but reliable in terms of our server just dying and losing all the production data, just like this. Now, let's think, how can we read this data? So like I said, since the consumers, they keep track of their offsets, so they can just travel through this stream of records from left to right in whatever direction they want. If I want to read some data, let's say from the middle of the stream, or some very old data from a year ago, if I have a very, let's say, a long stream, I want to be able to pick up any offset and just read the next n messages from this specific position. Now, in our current implementation, we would probably need to reread the whole stream from the very beginning. So that doesn't sound too good, right? Reread the whole file from the very beginning. So how can we make it more efficient by reading the data at any point without opening and reading the whole file from the very scratch? Well, we can introduce the very basic concept of the indexes. So probably know the indexes, for example, from databases. The idea here is a bit similar, I would say. So for each of the messages that we store in the stream at this particular index offset, we additionally store the actual index in a separate file. And within the index itself, we are simply keeping track of the actual bytes used by this message. So let's say message number 1 at offset equal to 1 starts at bytes position equal to 20. So by having these indexes in place, what we can do is that whenever we store these messages, we additionally store this index in a separate file. So for each stream, we'll have this additional file with indexes in place. And when we read the data from the disk, let's say I want to read n messages from starting at offset 1 million, we are simply opening our index file first, jumping, let's say, 4 times, as long as we are using 32 unsigned integer for the index size, multiplied by the offset. And then we know, okay, so this is index number 100. This is position in bytes number equal to 1,000 bytes. And then we can just open the file with our, let's say, records in the stream from this very position and just read from this start position, right? So a very simple way to actually start reading from the expected position without having to read the file from the very beginning. So just indexing in an additional file. Okay, but that's all fine. Now let's talk about the networking, because since this is the streaming server, this could play a very crucial role in your infrastructure, somewhere in your project at work. Of course, we need to expose some sort of networking protocols. So let's say we are supporting TCP, UDP, whatever. We have a server, we have multiple clients. Some clients might produce the data, some clients might consume the data, some might be both producers and consumers. Now, from the code perspective, let's imagine how this server could look like. So let's say we have a server. Within the server, we have a collection of streams, or actually map of streams and map of clients. We might have multiple independent streams. Each stream will have its own unique ID. And now, whenever we want to append the data to the stream, on a side note, as you will probably realize already, it probably wouldn't compile, right? If you look at this code, we would need some mutable reference here, stuff like this. So it's more like for the learning purposes, not really for the compiling purposes. So we'll need to pick up the actual stream by its ID and append the message or messages to the stream. At the same time, if I want to read the message, I just get this stream by ID from this hash map and fetch the message from the stream. And we can do this for multiple clients being connected to our server. Now, and of course, in order to make it actually work, we need some sort of synchronization mechanism, right? So let's say we'll be using read-write lock, as we might have only a single producer writing to the stream at this point in time. And we might have multiple consumers reading from the stream. So there will be a read lock using this RW lock approach. And we might have multiple consumers reading data from the same stream at the same time. So a basic data synchronization mechanism in place. Now, when you work with the streaming infrastructure, there is a high chance that you've heard about something like a topic or partitioning. So topic is nothing more than just a fancy name for actually dividing your data or dividing your streams into multiple substreams. And all these streams should actually belong to some kind of same logical group. Let's imagine that you are building some sort of analytics system for tracking the user clicks on your website. And you have multiple websites for your customers. These customers have thousands of users at the same time. So eventually you might end up with, let's say, millions of events being produced per second, right? A lot of data. And you might have like multiple clients trying to handle this events data in real time. But if you try to append this to the single stream, you will quickly realize that there might be just, let's say, a single consumer of the particular microservice consuming this data. You cannot really have like horizontally scaled out 10 instances of the same microservice trying to consume the data from the same stream, because you will just end up in lots of duplicated data on your consumer side. So what you can do is actually you can introduce this concept of the topic, this logical group of the similar streams, and you simply create multiple partitions. So in general, you just create multiple streams which are logically grouped under, let's say, these click events. And then whenever you produce this event, this record, you just append this event to the particular partition. And whether this is applied randomly or using some round-robin load balancing mechanism, or whether you want to make sure that, for example, all the events coming from user with ID 1 should be appended to the same partition, so at least you have this partial ordering, you can do this easily, even with this simple algorithm like partition ID equal hash of the key modulo n, where n is our number of partitions. And at the same time, you might go further, introduce this feature of so-called consumer groups. And pretty much at this point, that's all about that you need to know and you need to implement to have some sort of streaming system running somewhere in your infrastructure. But So let's just take a look at how this will look like from the code perspective. So now we are not talking about the stream itself. We are talking about the topic. The topic consists of partitions, where once again, the partition is now just another name for the actual stream. And from the server perspective, we treat this partition as the unit of work, the smallest, let's say, portion in our infrastructure, piece of our infrastructure that we can use to make this, let's say, producer or consumer work parallel, right? So this is, the partitions are independent from each other. So we can parallelize the work, and the unit of work is, in this case, the partition. Now, at this point, you might already build some quite performant streaming system. But yeah, let's talk about the performance. And the performance is not just about having the highest throughput possible. I mean, it's nice if you can handle 10 gigabytes per second of writes or reads. If you have Gen 5 SSD, you can do this. I mean, I can do this at home and I can easily saturate my disk. But there is more to performance. There are tail latencies. Like if your system starts lagging at, let's say, P99, so let's say every 100 requests or every 1,000 requests or something like this starts introducing like very high spikes, it will hurt your system, it will hurt your users, it might eventually crash your system. So you also want to take care of these tail latencies. They are very very critical. And for some, let's say, domains out there like financial domain, it's even more important to have stable latencies than extremely high throughput. They would care more about having P99999 very stable than just having 10 gigabytes per second writes. And of course, there is, last but not least, there is a thing of like utilizing your computing resources in the most efficient way. So maybe you don't need to spend so many CPU cycles on doing this thing. Maybe you can just use less CPU or less RAM. So eventually, your users running the streaming server somewhere in the cloud, they will pay less for the virtual machines because you utilize these resources more efficiently. So let's start with the first thing. The first thing, which might be not that obvious, is actually how we can serialize, or even more importantly, deserialize the data. There's this concept of the zero copy deserialization. So the whole idea is that whenever we are using, for example, the CRD framework and you serialize data, and since this, let's say, library allows you to use different kinds of, let's say, formats like JSON, BSON, a lot of different formats, in order to make it work, it actually needs to, at first, of course, load this data, let's say, data from file somewhere to memory. And then in this memory, it needs to sort of reconstruct these serializable types into your primitive, into your structures. And it needs to do this through some additional copy. And this is the copy that we would actually like to get rid of. And the zero copy is pretty much all about being able to like directly reference these bytes. So it's like loading the data from your disk, right, to memory, and then just automatically, instantly deserializing this memory, this part of memory into your structs without additional reading and parsing the data into expected type. So you need to know in advance. You need to know in advance what this type will be. So at this point, the deserialization is pretty much just casting the pointer. So it's like being able to somewhat transform your reference to bytes array into your expected type without the additional cost. And how you can do this? Well, you can do something like this, just use some built-in send file from Linux, but you probably don't want to do this. But on a serious note, in a Rust at least, you could use, for example, Archive, which is a very nice library. They have very nice Rust books / tutorial how to do this with all the motivation behind the scenes. So you can use Archive, you can use Musli. There's quite a few libraries out there. And if you know what you're doing, you might actually build this on your own, right? Because the thing with the Archive is that, well, it will introduce some complexity. And especially if you are building, let's say, the tooling and you want to be able to support this transport protocol across different programming languages, you might end up with quite complex Rust bindings, for example, to be used in Ruby, Python, .NET, Java libraries. So if you know what you're doing, you can just try to do this on your own, as you can see here on this example, where we just provide the mutable slice of bytes. We're just casting the pointer, and we are just, like pretty much copying the data, which leaves behind this pointer. And from our perspective, we've seen that introducing the zero copy in our experimental branch, we've gained like 50% better writes and almost 2 times better read performance, which is a huge win. And at the same time, we've used less CPU and memory. So this can give you a lot if all your application does is just reading the data, parsing the data, and sending the data through the network, reading through the disk. So this can give you a lot. Another thing, let's talk about the syscalls. Of course, in the Linux space, but not just in the Linux space, we have this concept of the user space and the kernel space. So whenever we want to, let's say, do something related to the storage, our file, the hardware, or let's say to the network, we need to do this through the syscall. Now, let's imagine that. Let's imagine as if you were the kid, right? And you want to make a sandwich. Now, if you are, let's say, 2 or 3 years old, most likely, if you want to make a sandwich, you need to slice a bread first, right? So probably your parents won't give you a knife, right? You will have to ask your parents to slice the bread for you. So essentially, you are making a syscall to your parents. They slice the bread for me so I can make a sandwich, right? So it wasn't another pseudo make me sandwich joke, at least. So pretty much this is what's happening at this point. And again, it might be irrelevant to you, but at the moment you will start receiving thousands, tens of thousands requests per second trying to save data, you will quickly realize by measuring like what is hurting your app that all these syscalls that may take maybe a few microseconds to complete, they will start summing up, and now you will see milliseconds or even worse, seconds, just waiting on 10,000s or millions of syscalls to complete, right? So this can hurt you. Now, let's take a look at this example in our code. So we have our append method, which actually opens the file, writes the file, and eventually close the file for the built-in write mechanism, right? So somewhere like 3 syscalls at this point. Well, so what we can do about this? Well, we could, of course, make use of the file descriptors. And even if you take a look at the Kafka docs, they will tell you that you should probably increase this U limit to quite a high number. Because as far as I remember, what Kafka does, so when they have like lots of partitions, they will keep open file descriptor for each of the partition, right? So when you keep your file descriptor open for the whole time as your server runs, you will at least be able to get rid of opening and closing file all the time, which will also help you in getting rid of some potential nasty page kernel issues. So 2 syscalls less, let's say, but still there's, of course, the syscall related to reading or writing to the file each time. But, of course, this will give you some noticeable benefit. However, we can do better. Has any one of you heard of IO-Uring, maybe? Have you used it somewhere or just experimented? Okay, so IO-Uring is quite new. And by new, I don't mean it's a month old. It's just 6 years old, which is very new for the Linux. From the Linux perspective. So this is like an asynchronous I/O for Linux. So it's alternative for what you already have. And one of the best parts about IO-Uring is that this is the unified interface for both network and storage. So you can use it for, well, from the streaming server perspective, for everything we need. So streaming is like database. It's mostly about reading and storing data and just sending the data and receiving data through the network, right? Because there is like no additional business logic happening. So this is all you need to care about when building something like this. So it can help you like greatly reduce the amount of syscalls and also the context switches. We'll talk about this in a moment. And the whole idea is that it's based on this completion-based approach, where the previous ones are based mostly on this readiness base. So readiness base is all about asking your operating system, hey, is this file ready to be opened? Is it ready to open? Yes, it's ready. Please open the file. While with the completion-based, you simply tell your kernel, hey, let's say, read the data from this file or save data to this file, and you only got the notification back the data was saved or the data was read. Here is the data, right? So it's a bit of a different approach. And it's been battle tested by some solutions like Tiger Beetle. I encourage you to take a look at Tiger Beetle. They are written in Zik, so they are even more more hipster than us. And this is they do a lot of cool stuff. So this is fully open source project as well. What does it look like behind the scenes? Well, the IO-Ring is all about having this shared memory between the user space and the kernel space. And as you can see, we have these 2 rings. Hence the name IO-Ring, because we have these 2 circular buffers, ring buffers, whatever we call this. So the first one is the submission queue, and the other one is completion queue. So the way it works is that from our application, which of course lives and works in the user space, we make a call. So we put this request to the submission queue. The kernel receives this submission request, and it does something with it. Let's say opens the file, saves data to the file, transmits data to the network, and so on. So how this could look like from the code perspective? Well, this is the Mono IO runtime. I'll talk about this more also a bit later on. This is made by ByteDance, so the company behind TikTok, if I'm not mistaken, fully open source. So something different than Tokyo. So the way it works, as you can see here, is that we open the file, so a very similar, let's say, approach as if we were to use Tokyo or standard library. And then we create the buffer of whatever the data we want to, let's say, read or save. And as you can see here, we are just passing this buffer to this submission queue, and then we are just receiving this buffer back from this completion queue. And we can just, and let's say this buffer at this point is filled with some data, right? So this is pretty much how you, let's say, at this point at least, read the data using the IO ring approach. And another thing, another like very important thing about IO ring is that you can actually submit a batch of, let's say, write or read calls in a single submission. So instead of making, let's say, 20 separate syscalls, you can do it in a single syscall through a batch. So this can give you like really tremendous benefits when you're building an app like this. And we did some experiments about a year ago with this runtime, and we've seen like a great improvement when compared, let's say, to the Tokyo runtime. So yeah, this is very nice to work with. Now, another interesting thing, because I told you that the fsync is not perfect, and actually we might want to get rid of the fsync, and I'll tell you why in a moment. Have you ever heard / used about the direct IO? Okay, so the direct IO is a way of bypassing your kernel cache through this DMA, which is actually the direct memory access. So whenever you actually read or write the data, it goes through the CPU, which caches it because you can predict that, for example, you might want to read another block of data, so it can do good things for you. But given the modern hardware, given how fast the SSD are, most of the modern databases, at least, they are mostly switching to direct IO. Because by doing so, we can reduce these unnecessary memory copies, and we can actually, as the name states, directly write and read the data to and from the disk. So we can get rid of using fsync at all, because we don't have to, let's say, flash the data all the time. And it's not, let's say, as durable as if we were to use fsync. But the issue with fsync is the following. If you look up this term, fsyncgate, or even the whole title, errors on fsync are unrecoverable, you will find at least a single or quite a few interesting articles about how fsync led to losing the production data in Postgres or MySQL. And it wasn't, let's say, the fsync fault itself. It was more how the fsync can deal with the errors, or how, let's say, the Postgres was able to or wasn't able to deal with the fsync errors, because it's really hard to recover from the fsync errors. So what most of these modern infrastructure, let's say, solutions do, these databases and other things, they usually rely heavily on direct IO. They make use of clustering as well, just to make sure the data is replicated across multiple servers. And with direct IO, have a better control if the things just fail. So you just need to live with the assumption that your disk, it will fail. There's a small percentage of SSD drives that will eventually fail. So it's on you to actually be prepared what to do when it fails. So this is why it might be better to get rid of fsync, just use direct IO, deal with the errors, replicate the data, and you will be just fine with this. How can you use this in Rust? So it's pretty much all about just passing this to additional flags when you are reading or writing to the file, or opening the file in this case. On a side note, it doesn't work too well with Tokyo, because the Tokyo will not give you any meaningful errors when something goes wrong with direct IO. So just, at least at this point, forget about Tokyo when you're using direct IO. It's not the best to use them both at the same time. And of course, you need to be careful how do you read or write the data. You need to work in these blocks of 512 bytes or 496 bytes, but then you can achieve much better, you will be able to much more efficiently use your hardware and directly write and read the data from the disk without the need of using fsync. Okay, another thing, the context switch. There was already mention of the context switch. So how our computers work, especially if we were to have just a single core in our PC and we want to be able to run multiple tasks at the same time, we have to run them concurrently, meaning that our CPU must stop, store the current task, stop it, switch to another task, restore then previous task data from the cache, and so on and so on. And well, just like with the computers, it's same for us, for the humans, right? Whenever we work on something, whenever we do something, we do it most efficiently when we are not interrupted by anyone else. So let's say if I were to write the code at this moment and someone would call me, I would have to store my state, like what was I doing before I had to answer this call. I would answer this call, then I'll have to restore my state, and then I would start coding again. Or I could fool myself that I am able to, let's say, multitask this thing, and I would try to pick up and answer this call as I was coding. But actually, what I will be doing is I'll be just constantly context switching between talking to someone through the phone and trying to write the code, right? So this is what will happen on at least a single core CPU. Now, as you can imagine, it probably might have quite a huge impact on how our application behaves, how it works, how efficient or not efficient it is. So what can we do about these context switches? Well, let's take a look at the following example. So once again, we have our lovely append method. And at this point, we are trying at first to resolve the partition. So once we get the partition by its ID, we try to acquire this write log just to make sure that we can write some data to this partition. So there might be some sort of context switch depending if this log is actually contended or not. And well, there is another partition append with this message or messages invoked, and there is await because this is a asynchronous function. So again, there might be some additional context switch happening. Of course, this is not going to be like very slow operating system/kernel level context switch. This will be most likely some user space or let's say Tokyo runtime based internal, very lightweight, very fast context switch. But again, as you can imagine, once we start adding all these context switches, once we start having tens of thousands requests per second, we will see that, there is additional millisecond or second that we waste on these context switches. And well, what to do about this? Well, one could tell you, just write your code better, right? Just design your code so there is no context switches. Well, it's not so simple because quite often the context switches might be actually deeply rooted to the runtime that you are using. And given that we use, for example, Tokyo, which is a great runtime, it works great for web servers, these sort of things, it might not be ideal for building the infrastructure, given that it works on this with this work stealing approach, where we have, let's say, multi-core CPU, and we have these queues of tasks assigned to each CPU. But in order to, let's say, keep our cores busy, so they don't just sit idle when there is more work to be done, the Tokyo might actually, let's say, steal the data from the queue, which lives on another core. So we cannot really control this unless we manually spawn these threads or just run this in a single-threaded approach. So what we can do about this work stealing or these context switches? Well, guess what? We can just switch the runtime. As I've already told you, even with direct I/O, which doesn't work well with the Tokyo, and with I/O uring, which is available to be added to Tokyo, but it's also not, let's say, the best, most efficient implementation, to put it kindly, we can switch the runtime. But before we switch the runtime, let's think about what is the potential alternative to this work stealing model. So there's this concept of thread affinity and thread core. So the thread affinity is all about making sure that particular tasks or parts of code will be actually bound to be executed on a very specific core instead of any of the available cores, right? So we want to make sure that, let's say, the specific task will be always executed on thread number 1, right? It will never be executed on thread number 2. Or let's say the partition will be only read or write to from this particular thread, not from any other thread. So we can avoid these context switches. And by thread affinity, we typically, what we have in mind is the so-called CPU affinity, which is mostly referred to as pinning your threads to cores. So let's say, as you can see in this simple diagram, what if we could just have pinned single thread per single core? So we have this thread per core approach, meaning that there is, let's say, no way to try to somehow share the data between these different threads running on a different cores. And what we can do about this in terms of our, let's say, database or message streaming system? Well, we could then somehow pin our topics, or even better, our partitions, which are, once again, the unit of work, like the smallest unit of work, which allow us to parallelize these reads and writes. So let's say topic 1, partition 1 will be pinned to thread 1, which is pinned to core number 1, right? And I can actually pin different partitions from the same topic across different cores, because once again, this could be independent. And at this point, we can get rid of many very costly context switches. We can get rid of using arcs, some additional log mechanisms across these threads and cores, because we are now at this point, we can be sure that whenever we read or write data to this partition, it will never be able to reach, or it will never involve any other core than this particular one. And this can help us actually greatly reduce the amount of context switches. Maybe not to zero, but but very greatly we can reduce them. And of course, there is more to this, because at this point, you have to remember something about, let's say, what if there is a request coming to our server, let's say to CPU number 1, and it tries to access the topic to partition 2, which lives on thread number 4 at CPU number 4. Well, we need some sort of message passing or routing so that the thread 1 could redirect this incoming request to thread number 4, right? So this can get quite complex when you want to actually implement this. But one of the, let's say, famous, I would say, infrastructure pieces out there using this approach is the ScyllaDB, which is based on the C# framework. There is also Redpanda, which is a Kafka alternative written in C++, which is also heavily using the same C# framework, and this so-called shared nothing model, where you try not to share any data. So all these hot paths should be executed on a same core, on the same thread. And by combining all these things, like, let's say, IO ring, that will help you reduce the syscalls and context switches, direct IO, the zero copy, you can easily double or triple your server performance, while at the same time dramatically decreasing your tail latencies. And this is actually what your users or potential customers want. And on the screen, this is actually taken from the Mono.io repository. You can see how well this runtime scales once we have multi-core PC. And guess what? Mono.io is not just about IO ring. It's actually all about this thread per core shared nothing design with IO ring behind the scenes, so you get the best of the both worlds. But like I said, there are different runtimes. There's also Glomio and a few other ones. But from our experience, I think at least for now, we mostly like this one. So there is a bunch of other things that I could talk about, like other techniques like kernel bypassing, which is all about giving your kid the knife to slice the bread for himself. So you can actually do this with, let's say, frameworks like Data Plane Development Kit. So in our example, the kernel bypass would be all about being able to directly access the, let's say, network, socket, hardware in general, from the user space without a need of making a syscall for the kernel space. And there are tools out there, like, for example, the Aaron I mentioned before at the very beginning, using this technique to greatly speed up this packet processing at the network level. there is eBPF, and yeah, there is many more. But that's all I have for now. And yeah, we just hit our time limit. So thank you. There was a gray word called grazie, which means thank you, but apparently it's not seen there. But yeah, there was written thank you. So thanks.
Okay, so let's head to the questions. So we can also come here closer to see them. Can we? The first question is: can we just use kernel caching and mapping mechanism when writing messages to a file?
I remember. I mean, we did something with mapping because this was mostly done by one of our core developers, Hubert. So if he was there, I would tell him to explain himself. But there was, I mean, we did some experiments, but I think there was a reason we decided to go with direct IRO. I don't remember if it was about the performance or dealing with the errors. But yeah, we had some experiments with mapping, and I think there is still some pull requests related to this one. But I can tell you the exact reason we actually did this and decided to go with direct IO. Was it just more because it's more commonly used by the modern databases? Yeah, but I will tell him to explain himself, and I'll be happy to post your answer back.
Okay, next question. Sounds similar. Can't we just use kernel caching and mapping mechanism when writing message to file?
So I think it's the same.
Yeah, exactly. Yeah. Does Iggy have production deployments? If yes, how is the experience of operating it at scale?
So let's say we have a few, but more. Let's say it's small production deployment in a sense that, well, at this point we don't have clustering yet. I mean, we did some experiments with Raft, and now we will be switching to this ViewStamp replication. But then again, we had this on some experimental branch. And we just decided to work on this performance at this point because we have to redesign our storage model, how we store the files. And once we complete this, we'll jump back into the clustering. So for the full scale, like large deployments, probably not yet, or at least I haven't heard about them yet. But we have like a few small production deployments. Even at my current work, we use it internally for data sharing between some components. So as long as you just do the streaming in a way, just to quickly pipe the data between, let's say, multiple applications, and you are not worried about like potentially losing your data in terms someone comes and takes the plug of your virtual machine, you will be fine. But with the full clustering in place, which is not there yet, we can tell we have like huge scale production deployments. But this will happen for sure.
How does Iggy compare to Redpanda?
Oh, that's one of my favorite ones. So the Redpanda is, at least what they claim, they are the better Kafka written in C++. Just a question, how many of you have used Kafka, for example? Yeah. So do you like it, or do you feel like it could, yeah, okay. So you're, yeah, okay. So the Redpanda is, let's say, the C++ alternative for Kafka using the same protocol. So it's like a drop-in replacement for your Kafka client, right? Which should be better, more performant, more efficient. The Iggy, I mean, it doesn't compare to, we can't really compare it to the Redpanda directly because we are not following the Kafka protocol. And the reason is that I believe that after over a decade since the Kafka has been, let's say, implemented and released to the world, which happened long time, over a decade ago, as some internal LinkedIn workings, I think it's actually high time to, try out something new. And just like, let's say, the Tiger B2 did with their financial database, we are trying to do the same with the Iggy. So we don't want to be tied to some sort of legacy transport protocol and all these things that come with Kafka if we were to build another Kafka adapter. So we can compare only to Redpanda in terms of, let's say, the performance. So the API is similar. You have the streams, you have topics, you have partitions, you have consumer groups, consumer offset. All these things are there. But in terms of the, let's say, architecture, we are a bit different. But I have to say that Redpanda is actually using this shared nothing model. I think they also use the IOU ring. So this is also something that we are planning to implement. But at this point, since we can only compare with them on a, let's say, single node level, we are already outperforming Kafka. I mean, especially quite a lot when it comes to latencies. And we were able to also beat the Redpanda in a single node comparison when we did some tests on AWS using the same setup, or at least the instructions they gave us how to run their benchmarks. So that's all I can say. So it's similar in terms of what the tooling is, but it's very different in terms of what APIs are used behind the scenes, and that we are just something totally different than Kafka. There's like no Kafka in Iggy code at all.
How hard is to spin up Iggy? Are you on Docker yet? I'm wondering about ease of use compared to starting a local Postgres server to tango with Iggy.
Yes, we have Docker images. And since we've transitioned to this Apache incubator, which was over a month ago, we are now also moving our Docker Hub repository under official Apache repository. I mean, we still have our current, I think it's Iggy.rs/Iggy Docker images. So if you just open our GitHub repository, you can, find all this info, but it's actually very easy. You can just pull a single Docker file, expose the port, and that's pretty much it. We have a bunch of examples in the repository related to building a very simple or a bit more complex, like let's say multi-tenant consumer producer applications. We have some work in progress documentation about how to use SDK. So yeah, it's quite easy, I would say, to start with Iggy. And we also have a very vibrant Discord community. So if you like to use it, just feel free to join.
How did you learn all the details about message streaming platforms architecture? You referred many times to Kafka. Was it your own inspiration? How deep did you get into its source code? Were there any other inspirations? Thank you.
So I want to say that Kafka wasn't my inspiration. It was more one of the things that made me start this in the first place. I didn't actually look up that much at the Kafka source code. I was more of reading some of the documentation because I was using this at work, right? I was using this, I had a chance to use these topics, consumer groups, offsets. So it wasn't like that difficult to imagine how it would work behind the scenes. So of course, I had to read some documentation from Kafka or from some other tooling. And also back in the day, I used this Aaron, which is, let's say, state-of-the-art message streaming, extremely fast, extremely efficient, at the same time, very complex to set up. At least it was back then. This is actually what made me start working on this, because I wanted to have something which would be as fast, or at least almost as fast as Aaron, but at the same time, it could be used for generic purpose solutions, like you can use Kafka. So I didn't go too deep into the source course. I mostly read, for example, this Martin Kleppmann's book. I read some of his lectures. I watched his lectures on YouTube, this distributed systems series. I watched some other videos, just started reading some articles, and just started, implementing the code. If you look at the very first commit, you will notice that like every week or every 2 weeks, there was like total rewrite or everything. So after, I would say, half a year or maybe a year, or I would say close to 2 years, we are getting to something which looks like the desired solution, right? So it took us almost 2 years just to figure out all these things, to make them right, and we are still like in progress. So it's like a constant learning. But yeah, just to say it once again, I didn't go really that much into the source code. More like I read about all these concepts, but didn't look at the source code at all.
Why is batching messages manually better than having the OS handle it? We had these questions. No.
Do you mean like better than having the OS handle it? You mean like using this page cache or? Okay. So I think it's better because if you make it configurable, then the user, the person who actually, let's say, sets up this streaming server infrastructure somewhere in his cloud environment or whatever they're using this, they can decide like what kind of, let's say, durability guarantees they expect? Like, do they want to flush the data after every single message because they have to build some critical, safe software, right? So at first, we wanted to make this to be controlled by the user, so the user can decide whether it's more important to have, let's say, higher throughput, better latency, or just very durable storage, let's say, being flashed to the disk after every single message. So it was like pretty much the core reason. And like I've already told you with this, let's say, direct IO example, we've seen some nasty bugs with the page cache, especially given that I was able to test it on Gen 5 SSD. And yeah, it just didn't work that well. So we wanted to also avoid this unnecessary memory copies to the CPU and then back to the user space and disk. So yeah, this was like the core reason to just do this on our own, let the user decide what are the expected guarantees for the persistency, and yeah, let us handle the rest pretty much.
Okay, next question is from Rafał. You said that benchmarking is your first-class citizen. How does Iggy compare to Kafka in terms of compute memory, resource usage, any numbers, metrics that you can bring up?
Yeah, so actually, if you open our, whether it's GitHub repository or Iggy Apache org or Iggy.rs website, whatever, you will find this link to this benchmarks.iggy.rs, which is actually this platform that we built, which is of course open source. And you can browse through some different benchmarks that we run on different hardware, including, let's say, macOS, my Linux PC, some AWS cloud environments. So here you can see, let's say, what kind of setup we run, what were the parameters, the configurations. And especially on AWS, we run the exactly same config that Kafka and Redpanda did in their benchmarks when they were comparing it themselves with each other. And I think this is AWS i3 Gen or i5, i6 Gen, something like this. You will find our numbers, and then you can look up the numbers from the official benchmarks done by Redpanda and Kafka, and you will see that we just got better results especially in terms of tail latencies. So yeah, I mean, at this point we can reach very high throughput and quite good tail latencies, but there is still lots of work to be done to make it even better. But even at this point, we're able to beat some of them in a single node mode.
Okay. The next question is from Maciek. Isn't the fsync and cache paging helping with situation when clients are not lagging and can just use cached values?
So yeah, I think it's a similar question, but once again, I mean, the core reason that we're actually getting rid of the fsync is that it's very costly. I mean, whenever you call fsync, it takes a lot of time to flash this data into your hard drive. Yep. Mm-hmm.
Large epic CPUs, which have like multi-gigabytes to RAM, to caches. So it's like the idea is that you write to the disk, but when you read it on the customer side, you never reach the disk.
Okay. So you could read it from the cache. Let's say if you're operating on a very fresh data and
leaf through this throughput without this cache layer.
Okay. Yes. So once again, we did a bunch of experiments here, and actually, just with having the file descriptors open, I was able to pretty much reach the limits of my Gen 5. I was able to hit this 15 gigabytes per second reads without using any cache. I was only caching the indexes, which are like very small thing. It doesn't take a lot of memory. So, I mean, we also have this setting for where you can set additional cache for your messages in your RAM. So let's say you can set 5 gigabytes of cache, and then this will be evenly split across your messages so that the client will read data from your RAM. But we've noticed that it's not that huge of a difference. You can still do it, but with a fast enough hardware, it's so fast that it's not like 100 times better. It's maybe, at this point, 20% better, maybe something like this. So it's not that huge of a difference. And I do believe that once we get back to the direct I/O and to I/O ring, it's going to be like almost negligible. So we just rely on a pure. I mean, you can still use cache. You can just still configure the cache, but if you just have a fast hardware, you don't even need caching. And I think this is also what Redpanda does, as they rely heavily on direct I/O, and they can give you the data, read the data for you very, very fast. Yeah, I mean, this will give you some boost, will keep this in memory, but it's not like a huge boost, because at the end of the day, if you are able to saturate your disk, most likely you are able to saturate your network. Let's say in AWS, the highest network is about 200 gigabits per second. So it's, let's say, 25 gigabytes per second, right? So it may sound like a lot, but it still, even with keeping all your data in RAM, you'll quickly saturate your network anyway, right? This will be limiting for you.
How data migrations work in Iggy when cluster is down and we have data there? What procedures or mechanism exist to secure copies of partitions?
Well, the cluster cannot be down because cluster isn't there yet. Isn't there yet. But so I cannot answer this question at this point. All I can say that we'll be most likely following some of the solutions already, let's say, implemented by the Tiger Beetle. If you look up the Tiger Beetle and if you read about the view stamp replication and the so-called protocol awareness recovery, you can read you'll find some very interesting techniques to ensure that, your data is here, including some additional checksum, cryptographic secure checksum to make sure the data wasn't tampered with, all these sort of things. So at this point, just look up Tiger Beetle or view stamp replication, how they use it. And there's lots of interesting articles around this.
Is it Hadoop ready? Question from Rafa.
No. But in terms of any other extensions, we have a plan to build some sort of connectors, integration / plugin mechanism. So just like in Kafka, you'll be able to, let's say, for every message, push it to some other data storage or stuff like this. So there will be some things in place, that's for sure.
Now we have a question and some correction of the question. How hard would it be to migrate up from Tokyo to Mono.io?
I think it was.
Yeah, Mono.io, because the second
it's not Monica. Depends on the app. If you are building like a regular web server, like a backend stuff, API, I don't think there is a point. You can do this for fun, but Tokyo is so good that if you know the Cloudflare company, they built Pingora purely on Tokyo, and they replaced Nginx with it, as far as I'm aware. So Tokyo is great. If you want to, let's say, migrate your app to the Tokyo, you have to make this, let's say, mental switch to this shared nothing design, because this is how you'll make most of this framework, because it will ask you to, let's say, set up the number of threads when you start this, and then you need to know how to, let's say, route these requests across different threads. Of course, Mono.io has some built-in HTTP servers. They have, I think, some schemes for working with Axiom or Hyper, or they even have their own HTTP server. So in theory, you could do this quite easily, but you just need to totally change your mindset in how you design your app. That you have some sort of specific, they call it shards, let's say shards or parts of your system. They work independent of each other. They don't share data with each other, and then you need just additional message passing mechanisms between these shards if you want to somehow, let's say, reuse the data or share data between them. So it's more of a mental switch than a huge amount of refactoring.
And the last question, how in real software engineering process you do comparison of multiple iteration of performance metrics in Iggy? Example, you switch from direct I/O to Mono.io. What tools or methodologies of measurements performance works?
Okay, so just to clarify, we didn't switch from direct I/O to Mono.io. We are still using the direct I/O within the Mono.io itself, because it's just a way of reading data or writing data to your drive without the page cache in place. So we didn't switch from this. It's more about, let's say, in our case, switching from Tokyo.io to Mono.io. So, well, just like with everything else, we just started with the experimental branch where we kind of refactored all of the code we had to the simplest way the simplest solution using mono IO that would compile and would run without any further optimizations. We run the benchmarks because this is also why we build this benchmarking CLI, all these things to be able to quickly, do any changes in the code, run the set of benchmarks and see if we are following in the right direction or not. So we just run a bunch of benchmarks and we're able to instantly tell that this performs better. Even though we just made the simplest refactoring ever, just to make it compile without any further optimizations, it just runs better. It has better P99 latency. So most likely this is the way to go. And given this is used in ScyllaDB, in Redpanda, and probably in many other infrastructure out there, it's probably worth trying. Because for some reason, all of these tools, they don't really rely on page cache. They don't rely on this work stealing model. They do things differently than we do when we build like a typical backends APIs.
Okay, that was the last question. So thank you for your talk.
Thanks.